Let us get started. So, we were looking at solving this 1D problem, which was basically we had a heat conduction problem, right, where there are 5 cells with the given boundary conditions 1, 2, 3, 4, 5, and then we had a isothermal condition on the right hand side, and there is a heat flux condition that is given on the left hand side. We called the phases A and B the end phases. Okay. We have looked at how to discretize the interior cells. We have also looked at how to discretize the right boundary cell. The only thing that is remaining is the left boundary cell, for which a heat flux condition is given, right. That is the only thing remaining in order to solve this problem. Okay. So, this one we have not yet looked at. So, let us take a look at this. So, essentially if I were to redraw this, we have cell 1 and cell 2, okay, where the cell 1 we call it as P cell and the cell 2 is east cell, and this is our phase A, where there is a heat flux boundary condition that is given. Okay. Now, if we write the discrete equation, the flux balance equation, what would that read like? That would read as K east A east dt dx east minus K west A west dt dx west plus SC plus SP TP times what? Delta V equals 0, right. That is our discrete equation. Now, if we look at here, what is our east and west phases here? So, this is our east phase and this is our west phase. West phase happens to be the same as the phase label A, right, that we have chosen. Now, let us go back and again we introduce linear profile assumption for temperature. So, this would be K east A east times T capital E minus T capital P upon del x E, okay, minus we have a Kw dt by dxw times Aw plus this remains as it is, SPTP times delta V equals 0. Okay. Now, what is the definition for QA bar or QA? What is QA? Minus K dt by dx evaluated at W, or basically same as A, right. So, then I can replace the minus K dt dx here with QA, right. I can do that. So, if I can do that, then I am going to write the discrete form here, which is nothing but K east A east times TE minus TP upon del x E. What would this be? This would be plus QA times A west, right, plus we have SC plus SPTP times delta V equals 0, okay, right. So, essentially as you can see, because of the prescription of a heat flux boundary condition, we completely got rid of the flux term here, right. We do not have TP minus T west like we had before, okay. So, that is not there. Now, if we rearrange in the original form, which is basically TP times the coefficients, that is TP K east A east by del x E, we are sending all the coefficients of TP to the right hand side, minus SP delta V equals T east times K east A east by del x E plus T west times 0, we do not have a coefficient to the west, right, because that is where the boundary condition is there, plus we have QA times AW, that is the heat flux boundary condition that is already known, right, this is already known, times the area. Then we have this would be plus SC times delta V, right, that is what we have. Okay. So, now if I were to write again in the coefficient form, this would be APTP equals A east T east plus plus some B, right, plus some B, okay, where A east is nothing but K E A E upon del x E. What would be AP? AP would be east, there is no A west is 0, right, there is no A west is 0. So, this will be A east minus SP times delta V. What would be B? B would be SC times delta V plus QA times AW or AA, right, both are the same. That is what we have, because Q is known, cross sectional area is known, these all go to the right hand side, right, these are all known. Okay. So far so good. Now, what about the Scarborough criteria? If we have a Neumann boundary condition, what about Scarborough criteria? For a particular cell that has a heat flux boundary condition, what is AP now? Is it greater than, let us say if we have a source is 0, S is 0, in the absence of sources, what is AP? Equal to AE, right. So, this only satisfies in equality, does not satisfy in inequality, right. If there was a source, then this would be AP would be greater than A east, right, because SP, if I assume that SP is less than 0, in which case AP would come out to be greater than A east, right, which it satisfies in inequality as well. Okay. Now, what does it mean? Let us say if we have a problem, okay, if I kind of go back to the problem statement and I say that instead of the constant temperature condition here, that is instead of this Dirichlet boundary condition, if we also specify a heat flux here, if we specify QB, okay, if I specify QB here, okay, being applied on this right face B, then what will happen to the Scarborough criteria for all these cells? For the interior cells, we said if let us say source is 0, okay, for all the interior cells, if the source is 0, Scarborough is satisfied in what? Equality, right, it satisfies in equality. What about the boundary cells now? It will also only satisfy in equality, right. So, then are we actually satisfying Scarborough criteria in inequality anywhere for any of the cells? We are not, okay. Then of course, the question that pops up is, well, will this converge, right, and it is completely physical, right, it is physically possible to have two heat flux conditions, right. Let us say you have insulated on one side and providing heat flux on the other side, then if I want to solve it numerically, can I solve it? Yes, you can. So, what you realize is that out of the two Neumann boundary conditions that you have given, there will be one less equation, essentially one of these equations will become dependent on the other one, okay. So, out of the 5 cells you have, up till now you have 5 independent equations for all the 5 cells, then what you realize is the moment you specify all the heat flux boundary conditions for the problem, you will get a you will get a rank deficiency, okay. Essentially, that one of the equations that you get out of the 5 will be dependent on the other equations, okay. So, as a result, you will only have 4 independent equations, okay, and you will be able to solve, then as a result you will satisfy Scarborough because one of the cells would come out to be a known value, okay. In that context, you will be able to still satisfy Scarborough and get an answer using an iterative method or a direct method, okay. This we will probably see in a particular assignment problem or something like that, okay. I will try to set up a problem like that. Fine, is it clear? Okay. Questions till now? If I have two Dirichlet boundary conditions, let us say if we specify TA and TB, what will happen? And in the absence of sources, do we satisfy Scarborough in inequality and equality? Yes, we do, right. All the interior cells satisfy in equality and the boundary cells will start satisfying in inequality and the problem converges without any issues, right, because you get a diagonally dominant system. Okay. All right, let us then move on. So, what I plan to do is we will look at the steady diffusion equation in 2 dimensions, okay. Then also look at the boundary conditions thereof. Then we will come back to a discussion on how to calculate diffusion coefficient on the faces, okay. That we will come back once we finish the diffusion equation in 2 dimensions. So, this is steady diffusion equation in 2 dimensions and we are still looking at structured meshes. Okay. We have not discussed, but we are actually looking at structured Cartesian meshes. Okay. So, essentially structured Cartesian meshes or is what we are looking at implicitly, right. Okay. So, how does the steady diffusion equation in 2 dimensions read? It will read the same as the previous one. Essentially what you have is you have del dot gamma grad phi plus S phi equals 0, right, where your del bar is now because you are in 2 dimensions, this will be I partial partial x plus j partial partial y, okay, that is your nabla operator. Then we have to have a domain to discretize this equation, okay, on the particular cells. So, I am going to draw a particular domain here. The domain we choose looks like this. Okay, so this is my, so this is a domain that is discretized. Okay, so this is the mesh. Just like before, we would like to call our cells. So, we call this as P cell, and we call this cell as east, this as west, this as our north, this as south. Okay, and then essentially we have x and y coordinates aligned in the Cartesian axis. Okay. All right. Then we also of course need to have dimensions for the widths of these things. So, this is essentially we have a width of delta x for the P cell and delta y in the y direction for the P cell. Okay. We also need other dimensions, that is this distance, that is between cell centroid of P and capital E would be del x E, just like before, and this distance between P and W would be del x W. Okay. Similarly, the distance between cell centroid of P and north would be del y north, and between P and south cell centroid would be del y south. Okay. So, we have all these widths for the cell P and for the distances between the respective cell centroids. Okay. Of course, we have to also identify the faces which lie between these cells, and they happen to be I will use so this will be face E, east, which lies between P and capital E, and this would be the west face, little w, this will be the north face, and this will be the south face. Okay. So, we have east, west, north, south faces which form this cell, primary cell P. Okay. That is all. Okay. Now, we are ready to start discretizing the equation. That is, first step is to integrate the governing equation on the control volume for cell P. Okay. So, essentially that leads us to integral control volume del dot gamma grad phi dV plus integral control volume S phi dV equals 0. Okay. Okay. Now, what do? We invoke Gauss divergence theorem. And going to convert this volume integral into a surface integral. So, this will be control surface gamma grad phi dot dA bar plus integral control volume S phi dV equals 0. Okay. That is what we have. Now, what is this control surface in this context? Control surface is now made up of 4 faces, right, the 4 faces, that is the east face, the west face, the north face, and the south face, right. So, this is our control surface. Okay. And we assume that the control surfaces are planar, and this value, the gamma grad phi that we have here, okay, if we evaluate at the face centroid, okay, and that value prevails over the entire phase. Okay. If I assume that, then this is a constant for a particular phase, okay, then that constant I can integrate and then replace this integration with a summation, okay, and that summation would lead to now a discrete form of this integration, that is nothing but sigma on all the phases gamma grad phi evaluated on the respective phases f dot a f bar. Okay. So, we have replaced the integration with for this dot product of gamma grad phi dot dA bar with a summation on all the phases gamma grad phi f dot A f bar. Okay. Now, what are the phases that we have? F goes from little east, west, north and south. Okay. So, we have these 4 phases, plus we have already also said that S phi has to be evaluated for the entire cell, right. We need to calculate what is S phi dV, and if we assume that S phi, the value of S phi at the cell centroid prevails over the entire cell, then this can be written as some average value of S phi bar calculated at the cell centroid times delta V equals 0. Okay. Now, what is so each of these will be the sub f here would change from east, west, north, south. Okay. So, what will be vectors A east, A west, A north and A south? So, if I go back, what will be the vector A east bar? So, we assume that all the area vectors point outside, okay, out of the cell. So, what will be AE bar? AE bar would be I would be the point direction which is pointing. What will be the magnitude of the delta y, right? Delta y is the area, right, delta y times I, right. So, AE bar is essentially I times delta y, it's pointing in the positive x direction. Is there a component in the j direction? No. So, essentially 0, right, we do not have a component. So, that is 0 plus j times 0. What will be A west bar? Minus I times the, what is the magnitude? Delta y, right, it is the same square cell, rectangular cell. Okay. So, this would be minus I times delta y. What about A north? Delta x is the magnitude. Okay. So, we have heat here, delta x is the magnitude and it is pointing in which direction? J direction. So, this is A north bar. So, this would be, if I were to write, this will be j times delta x plus I times 0, right. We do not have any component in the I direction. What about A south? It will be minus j times delta x, right. If you like a bar, I will put a bar on this. Okay. So, these are the area vectors for the primary cell P. Okay. Now, what about delta V? We have this guy delta V, which is the volume of the cell in 2 dimensions. This would be delta x times delta y times 1, right. It is anyway 2-dimensional problem. Okay. So, essentially we are doing this because we have to now evaluate this dot product of gamma grad phi on let us say on the east phase and for the west phase and so on, right, and then we have to make a summation here. So, that is why we are doing all this. So, let us look at the first component. So, that is in the summation, that is gamma grad phi east dot AE bar, right. This is the first term that we get in the summation. What about gamma grad phi east? This is nothing but gamma east, grad phi is I partial x plus j partial y. So, this will be I partial phi partial x evaluated at east, and then we have plus gamma east j times partial phi partial y evaluated at what? East, right, times what is AE bar? I times delta y. Okay. So, which term survives out of this inner product? Only the first one, right. We do not have a j component here. So, essentially it is a dot product, only this guy survives. We do not, this guy will not survive because there is no j component there. Okay, easy. Then this will be what? Gamma east delta y partial phi partial x e times I dot I, that is 1. Okay. So, we have this term that survives, simple. Now, without actually calculating this way, you can now guess what would be gamma grad phi west dot A west bar. Gamma west delta y partial phi partial x evaluate w with a minus, because this comes with a minus I bar delta y. Okay. So, we can write that. Okay. Now, very good. Let us move on. What would be gamma grad phi north dot A north bar? So, if it comes to north, I can write it here just for convenience. So, this will be gamma north I partial phi partial x north plus gamma north j partial phi partial y north dot what would be A north? J times delta x, right. So, the only term that survives is the j component term. Okay. So, this term does not come into picture. So, as a result, what would be gamma grad phi north dot A n bar? Gamma north delta x partial phi partial y evaluated on north. Okay. So, similarly, gamma grad phi s dot A s bar would be how much? If you can, it will be a minus gamma little south times delta x times partial phi partial phi partial y evaluate on the south face, right. Is this correct? Yes. Okay. So, essentially what we did is we have evaluated all the 4 terms for all the 4 faces that come out of this gamma grad phi f dot A f bar. Okay. That is what we have done. We have to basically sum all these guys. Okay. And then I am going to use the same linearization for the S phi bar. Okay. So, I am going to use a linear source model, okay, which would tell me what is S phi bar equals SC plus SP phi p. Okay. So, we are going to use this source model, fine. So, if I were to put all of these back, what would that be? The equation would be gamma east delta y partial phi partial x east minus gamma west delta y partial phi partial x west, right. That is what we have here, right. The second term is here. This is the first term, this is the second term, third term and the fourth term, right, in the summation that we have here. Okay. So, this would lead to plus gamma north delta x partial phi partial y on the north face minus gamma south delta x partial phi partial y on the south face, right. That is the first term, plus we have SC plus SP phi p times delta V is now what? Delta x delta y equals 0, right. Is it correct or any mistakes in here? Fine. Okay. All right. Now, what do? We have to introduce, so we got the phase fluxes, which are the partial phi, partial x, partial phi, partial y terms. These we have to express them in terms of the cell centroid values. Okay. For that, we are going to make a linear profile assumption, okay, and express these guys, that is gamma east delta y partial phi partial x east as gamma east delta y times phi capital E minus phi p upon what? What would be the distance by which this is changing? Del x E, right, because that is the distance between the cell centroids. We are looking at phi capital E, we are looking at phi capital E here and phi p minus the distance is del x E. Okay. All right. So, similarly, what about gamma w delta y partial phi partial x west? This will be gamma west delta y phi p minus w upon del x w. Okay. Okay. What next? Gamma north del x partial phi partial y north, right. This would be how much? gamma north delta x times phi north or p? North minus phi p upon del y north. Okay. What about gamma south delta x partial phi partial y south? Gamma south delta x times phi p minus phi south upon del y south. Okay. Is this clear or any questions in this part? Essentially the same linear profile assumption, instead of in the x direction we have now applied in the y direction as well. Okay. Alright, this is simple. Now we all have to do is we have to plug these things back into this equation. Okay. So this is our discretized equation. So this is our kind of discretized or the flux balance equation, which will come back a little later. Okay, so as you can see there is a minus for the west and the south terms, so that we have to consider while we plug in these quantities. Okay. Now can you plug in these quantities into the equation and club or essentially separate the terms as the coefficients for phi p and the coefficients for phi east, phi west, phi north, phi south, and write it in terms of A p phi p equals A east, phi east, and so on, right? Can you work on that and tell me? So plug in all these quantities back into the discrete flux balance equation and rearrange the terms such that we get our original equation. Okay. So essentially substitute the flux terms into the discrete equation and rearrange to get the finite volume formulation. What will be the coefficients for phi p? So essentially collect all the coefficients for phi p and then send them to the right hand side. Okay. What are the coefficients, anybody, for phi p? Gamma east delta y upon del x e, right, plus gamma west delta y by del x w plus gamma north delta x upon del y north plus gamma south delta x upon del y south. Okay, now if you write the remaining east, west, north, south on the other hand, oh, plus source term, okay, minus, okay, very good. So this will be minus SP times delta x delta y, is that correct? Fine, okay, and equals on the right hand side what we have, phi east times gamma east delta y by del x e plus phi west times gamma west delta y by del x w plus phi north times gamma north delta x by del y north plus phi south times gamma south delta x by del y south, right, plus SC times delta x delta y. Okay. So these are, that's all, right, that's all we have. We don't have any other minus other than the minus SP delta x delta y term. Okay. So this, if you have not done, you can do it and then check this part. Okay. Essentially verify that you get this equation. Fine. So we want to put this equation back in the original form, that is A p phi p equals A east phi east plus A west phi west plus A north phi north plus A south phi south plus B. Okay. So we have written all these equations. Now one thing we have to keep in mind is that we are multiplying the neighboring values, that is the phi east, phi west, all these things, right. These are all the cell centroid values. The coefficients, when I am writing, I am using a capital E, okay, to indicate the coefficient for phi capital E, but we realize that this coefficient actually depends on where? On the phase, right, because it contains gamma little e delta y by del x e. So, this actually is evaluated the phases, okay, that have to be kept in mind. Okay. Now, what is of course, we can explicitly write it down. I am not going to write all of them, but going to write A east, A north is gamma north delta x by del y north, and so on for the other coefficients. And what is B? B is SC delta x delta y. Now, what is AP? AP is, if you look at here, it is A east plus A west, A north plus A south minus SP delta x delta y. Okay. So, this is nothing but sigma A and B, where NB I would like to write it as a neighbor east, west, north, south, okay, sigma A and B minus SP times delta x delta y, okay, where I am writing NB as a short form for neighbor. Is that correct? AP equals sigma A and B minus SP delta x delta y. Of course, we can also simplify our equation in terms of NB. I can write this as AP phi P equals sigma A and B phi and B plus B, right, where NB is basically capital E, W, north and south, okay. So, this is our final linear equation, the discretized linear equation, which we have to write one such equation for every cell, and then we have to use some linear solver to obtain the solution for phi all over the domain, okay. Questions till now? Is this part clear? Now what you see is, because all the phases are aligned with the x and y axis, we did not get any cross terms, right. For example, east is always evaluated, you know, the east phase always had this x derivative, it never had the y derivative, right. These things never came, right. Otherwise, earlier when we started off, we had these terms, right. We had on the east phase we had a y derivative, but that never showed up, right. Similarly, on the north phase we had a x derivative and a y derivative, but the x derivative never showed up, right, because they all kind of disappeared. Why did all these terms disappear? Because the mesh is not only structured, because the mesh is orthogonal, okay. Essentially it is orthogonal, yeah, it is kind of Cartesian meaning it is orthogonal. That means your area vector, right, that you have is aligned with one of the coordinate directions, right. That means the line joining the cell centroids, right, that is your area vector, is aligned with one of the coordinate directions, okay. Or in other terms, essentially the area vector of the face, okay, is parallel to the line joining cell centroids. Okay. That means, if you are going to draw a line between P cell and east cell between the cell centroids, this line is aligned with the area vector that we have, okay. It is parallel. So, these kind of meshes are known as orthogonal meshes. We will come to this little later as we look at the unstructured meshes, okay. If these two are parallel, then we have an orthogonal mesh. As a result, you will never get these cross terms, right, they will always drop out. Otherwise, you end up with these cross terms as well, okay. So, that is one thing we have to keep in mind. Alright, let us look at some comments on what we developed, okay. So, let us look at some comments for the 2D diffusion equation. Okay, what is the first comment? The first comment is, of course, similar to the 1D case. If we go back, the discretized equation that we have here, what is this? This is an equation, this has some physical significance, right. What is it indicating? It is indicating the flux, that is gamma east times partial phi partial x times the area, flux times the area terms, right. So, this is all flux times the area is balancing the source that is getting generated, right. That means the flux that is leaving times the area out of the east phase minus what is entering through the west phase, and whatever is leaving through the north phase minus whatever is entering to the south phase is balanced by whatever is generated inside. Okay. So, that is basically we have a there is the discrete equation is an equation for flux times area balancing the source within the cell, right. So, this equation is a conservative statement or a statement of conservation, okay, which tells whatever is leaving or entering through the cells is balanced by whatever is generated within the cell. Okay. So, that is something that we need to look at. Then we have of course introduced for the gammas and for the fluxes that we got on the phases. So, we have introduced a linear profile assumption, right. Of course, we have also introduced a profile assumption for averaging for SV bar also, we have also linearized this thing. So, the diffusion coefficient, the fluxes and the source terms, we have introduced a model that is a linear profile assumption or a model for all of these things, and we connected the phase fluxes that we got similar to the 1D case, we connected it to the cell centroid values, right. By introducing this thing, we connected this to cell centroid values. Fine. Now, because we have a statement of conservation, the finite volume method always gives conservation irrespective of mesh density, right. If we take coarse cells or if we take fine cells, it is always going to give conserved solution, okay. But of course, it may not be accurate. So, that we have to see, may not be accurate though. That we have to see depending on the accuracy that we want, but otherwise because phi is found from this by satisfying this discrete equation, it always gives a statement of conservation, okay, all right. So, we have a statement of conservation here. Now, what else do we have? We have in terms of properties, okay. Then what about these coefficients, the coefficients that we have, that is A east, A west, A north, A south and AP. What are these signs of these coefficients? A and B are always positive. What about AP? AP is a summation of A and I bus, and there is minus SP, and we said SP is always, I am assuming SP is negative. So, this is, they have the same sign, okay. So, essentially AP and A and B's have same sign, okay. Now, what does it mean if they have the same sign? If they have the same sign, because we have AP phi P equals sigma A and B phi and B plus some B, okay. If I have the same sign for A and B and AP, okay, if my phi and B, that is the phi for east, west, north, south or something, it goes up, what will happen to phi P? Would it increase or decrease? If these increases, they have the same sign, what will happen to phi P also? Increases. So, essentially if this increases, right. This is a property that has to be satisfied for elliptic equations. For example, in an elliptic equation we have discussed this, in the initial lectures, that if there is a disturbance somewhere, it has to propagate in all directions, and the properties should be, the final phi should be smooth everywhere, okay. So, as a result, because these have the same sign, as phi and b goes up, phi p goes up. So, this is a property of elliptic equations which is now satisfied by the discrete equation that we have developed. Okay. That is one property. The other property is in the absence of source terms, let us say S equals 0, okay, S equals 0. What is AP? AP is sigma A and B minus SP times delta V, but we have said that the source is 0, S is 0. So, what is AP? AP is simply summation of sigma A and B. Okay. Now, what does that mean? What that means is, if we rearrange this equation, if I were to write phi p, that is the for the primary cell, this would be sigma A and B by AP times phi and B plus B is now 0, okay. I do not have source term, so this is 0. Okay, now I got some equation here, but what is my AP? Sigma A and B. Now, what does this equation tell us? This tells us that phi p is a linear combination of all the phi and b's, right, and because A and B by AP, this will always sum to what? This will always sum to 1. So, phi p is always bounded by phi and b's, right. Now, I use this word called boundedness, okay. So, this is bounded. So, phi p is bounded by phi and b's. What does it mean? That means the phi p value that you are going to get will be somewhere in between or equal to phi east, phi west, phi north, phi south, right. That is because the fraction, the coefficient that it is multiplying is satisfies this equation, right. Sigma A and B by AP, this equals 1. That is why this is bounded, right. That means if you have let us say several values, let us say you have 300, 400, 500 and let us say 100, what will be a possible value for phi p? Can phi p be 700? It cannot be, because it can never be greater, because we do not have a source term. So, this will be somewhere, this cannot be greater than what? Cannot be greater than 500, right, and can it be less than 100? It is not allowed to be less than 100. So, it has to lie somewhere between 100 to 500, right, between the max and the min. It has to be bounded somewhere between 100 to 500. That is what this equation ensures. Now, this is another property of the elliptic equations, right, because you have this smoothness, as a result of which in the absence of source terms, your solution should be bounded by the neighboring values. You cannot all of a sudden get some other value which is unphysical, okay. So, these are the two properties of elliptic equation which are now satisfied. These are the properties of elliptic equations which are now satisfied by the discrete equations that we have developed, okay. Elliptic equation, these satisfied by the discrete equations developed, okay. Now, if we have a source term, can it be larger? Yes, it can be, because AP is now not just sigma A and B, but you have sigma A and B plus something, right, that is minus SP delta V. Is that physical? That is physical. Let us say you have a heater somewhere in the room, and those places is where it will be larger than the neighboring values, right. So, that is completely physical, okay. So, that is in the presence of a source term, it is physical. Alright, now let us look at the Scarborough criteria. What does Scarborough criteria say? It says that sigma modulus A and B upon mod AP has to be what? Less than or equal to 1 for all cells and less than or equal to 1 for at least one cell, right. Let us say we do not have source, okay. Let us say S is 0, source is 0, then which of these is satisfied, the first one or the second one, by the equations that we have developed. So, if we do not have a source term, what is AP? AP equals sigma A and B, that is all. So, only equality is satisfied. Okay. So, essentially this is satisfied. What about inequality? If we have a source term, it will be satisfied. If we do not have a source term, it will not be satisfied. Okay. So, in the absence of sources, the inequality is not satisfied. Now, how do we make this satisfy? Through the boundary conditions that we have already seen like yesterday. Okay. So, if we have boundary conditions, then it may be possible to satisfy the second condition. Okay. So, that this Scarborough criteria is satisfied as well. Questions till now? The Scarborough criteria? Okay. The Scarborough criteria explanation, essentially you have, you know the condition, right? Sigma modulus A and B upon mod AP should be less than or equal to 1 for all the cells in the domain and should be less than 1 at least for one cell. Okay. Now, in the absence of sources, that is S equals 0, okay, we know that what we have developed is AP equals sigma A and B, right. This is what we have. That means, we are only satisfying this less than or equal to condition, right. So, for all the cells it will be equal to, AP would be equal to sigma A and B, but for none of the cells AP would be greater than its neighbors values, right, in the absence of source term. If there is a source term, then AP would be greater than sigma A and B by minus SP times delta X delta Y, or if there is a boundary condition, AP would be greater. Okay. So, in that context, the Scarborough will be satisfied for both 1 and 2 conditions, otherwise it will be only satisfied for the condition 1, right, it will be only less than or equal to mod AP, okay, or less than or equal to 1. Other questions? Yeah. Boundedness, okay. Question is about explain boundedness. So, take for example, few numbers, okay. Essentially you have A and B's, choose some numbers and choose AP as sum of all of them, okay. These are all positive and AP is summation of all the numbers. Now, what I am saying is the value of phi P that you are going to calculate from phi east, phi west, phi north, phi south would always be bounded by these neighbors, because the coefficients with which you are multiplying sum to 1, right, because this sigma A and B by AP is how much? This sums to 1. As a result, if you have taken some numbers, then this phi P would always come out to be limited by the neighboring values that you have, right. So, what I suggest is you can choose some A and B's and then see for yourself that these fractions would always make it to come between these values only. It will never be higher than this, or it will never be lower than, it will never be lower than 100, or it will never be higher than 500, okay. That is because sigma A and B by AP sums to 1, okay. As a result, we say that the value for the cell centroid is always bounded by the neighbors, okay. It is not more than it, it cannot be more or it cannot be lesser than the lowest value, okay. That is what I call boundedness, which I may refer to it from time to time, okay. Other questions? Clear? Okay. One thing we have not discussed is the problem, the 1D problem. So, essentially we have now set up equations for 1, 2, 3, 4, 5 cells, right. So, you have 5 equations and then you have to solve those equations using some method, that could be a Gauss-Seidel or a direct method and things like that, okay. Okay, then tomorrow I am going to look at the assignment, essentially quickly go through how to solve the assignment, and then I hope by tomorrow you will take a look at the assignment and come back with questions, then we can answer all the questions. Then we will start off with the boundary conditions in 2 dimensions, okay. So, we are going to look at the Dirichlet, Neumann and mixed boundary conditions and then move on from there, okay. All right, thank you.